Hello everyone, welcome to Prativa Tech. In this video, we will solve the problem of the day question on Geeks for Geeks for 20th November 2023. The problem statement for today is K sum paths, and this question has been asked in Flipkart, Amazon and Walmart interview. So let's now open this problem to solve it. Let's go through and understand the given problem statement. Given a binary tree, an integer k, find the number of paths in the tree which have their sum equal to k. A path may start from any node and end at any node in the downward direction. Okay. Since the answer may be very large, compute it modulo 10 to the power 9 plus 7. So the problem statement is simple here. It is saying that a binary tree will be given and one integer will be given, that is named here as k. We have to find the how many paths are computed to that sum that will be equal to k. Okay, how many paths and the path can start at any node and end at any node. So if you look at the given examples, so the first example says this is the given tree where 1, 2 and 3 are the elements here, and here k is given as 3. So here the output is 3. So here according to this statement here, and that there are two paths which can lead to sum as equal to 3. So path 1 will be 1 plus 2, that is equal to 3, and path 2 it will be only the leaf node 3. So one will be 1 and 2 and another one is only 3. So we have got two paths here which can lead to sum is equal to k, which is equal to 3. If you look at the given second example, so this is the given tree here, and here k is given as 5. So here the output is 8. So it is saying that total 8 paths are there which can lead to sum as equal to 5. So here all the 8 paths are given here. So first one is 3 plus 2, then 3 plus 1 plus 1, then 1 plus 3 plus 1 this way, then 4 and 1, then 1 minus 1 4 and 1, minus 1 4 2, 5 and 1 minus 1 and 5, this one. Okay, so here it is given that it is total 8 paths are there. Okay, so I hope both the problem statement and given examples are very clear. So to solve this problem, we will be using the approach of depth first search. Okay, so here we will be using depth first search traversal on the binary tree to find the number of paths which is equal to the given sum k. The logic here employs memorization by using a hash map to keep track of the running sum frequencies encountered during the traversal. This helps to avoid redundant calculation and improves the efficiency of the algorithm. Okay, so I'll tell you how it will be used. So this is the explanation I have taken for the first tree. So here when we start the traversal of this node, okay, so here we will first traverse with this root node which is equal to 1. So here the node data will be equal to 1. That time the map will be empty. Okay, so the current sum will be 1, which is equal to this one, this node value only. So now if we perform a calculation like current sum minus k, it will be minus 2. Okay, and here since minus 2 is not equal to k, it is not equal to k, so that's why the count is 0 here, and count after checking current sum is equal to k, that is also 0 here. Now when we move to the second node, so here the node data will be 2, and in the map whatever the current sum we got that time, so that time we updated in the map. So the map will now contain 1 and the count will be 1 here. Okay, so now the current sum will be 3, which is 1 plus 2, that is equal to 3. Now if we check here current sum minus k, this will give 0. So current sum minus k can give 0 when current sum will be equal to k. Okay, I hope this statement is clear. So here we are checking for the operation current sum minus k. Here it is giving 0. This can give 0 when both the variables have the same values. Okay, so till that point count was equal to 0. Now after we check that current sum is equal to k, then that time we will increment the counter value and it will be 1. The count after this check, since this will be true, because the minus operation is giving the value as 0, that means both are equal, so that time we increment the counter, it will be 1. Okay, now we will move to this third node. Okay, so map will contain this one right now, 1 is equal to 1 and 3 is equal to 0. Okay, so now we'll check the current sum. Current sum will be equal to 4. Current sum will be equal to 4 here, 1 and 3 here. So now current sum minus k, current sum minus k, that will give 1. And we'll check in this map, do we have anything that can give do we have any value in the map where the key will be 1 and where we have got some count. So we can see in the map here 1 is equal to 1, that means for value 1 there is 1 count. So that we will take into consideration, and we will add to the current count. Okay, so now the count will become 2. So here what we are doing, here we are using, that means till this point when we are performing this operation, current sum minus k, so whatever value we are getting, so we are checking if for that particular key do we have got some value in the map. So this will ensure that the previously computed value which was valid for this 1 is equal to 1, and we had got 1 count or as many count, 1 count in this scenario, or whatever count we get, so that it can be utilized later to for computing the further paths. So that's why we get that count and we increment it to 2, and after count we check the current sum is equal to k. So here it will be false, because current sum was 4 and k is equal to 3. So that's why we do not increment the counter here, and it will remain as 2, and after that loop will terminate and this function will exit, and finally we get the output as 2. Okay, so this was the given, this is the approach we are going to follow. This will be more clear when we go through the code, that how it is written. So let's minimize this one and let's go with the coding part here. So here first we will start with Java solution. I have already prepared the solution. Let me just copy it here. So here I have added comments as well, so that it becomes easy in understanding. Okay, so if you look at this complete solution, so here first we are defining this modulus value, because it was mentioned in the problem statement. If the answer is very large, then compute it, the answer modulo 10 to the power 9 plus 7. So that for that purpose it is here. And what we are doing here, inside this method, first we are initializing prefix sum frequency. This is a hash map used to store the frequency of the running sum and counter during DFS traversal. Then we have got one count array of size 1 to act as a counter for the result. Okay, then from here we are calling the method the DFS, and we are having these following parameters, that means root node k, then the value is the current sum which is getting passed, which will be equal to 0 initially, and these two things, count array and frequency. Okay, so when we look at this DFS method, so here actually this method was the entry point, and it initializes the hash map as I have told earlier, and a counter, and calls the DFS method to perform the depth first search of the binary tree. So when we look at this DFS function now, so this DFS function is a recursive function that traverses the binary tree for each node encountered during traversal. It updates the running sum, okay, this one, which is the value as the current sum, and checks if there is a previous running sum that makes the current path sum equal to k. So that we are checking first. Then it also increments the counter if the current sum is equal to k. The running sum frequency map, that is which is equal to this prefix sum frequency, that is updated including the current sum running frequency. This we are updating in this one. Okay, then the function then recursively calls for the left and the right subtree. Finally, it backtracks by removing the current running sum from the map to avoid affecting other paths, because if one it is getting used at somewhere, so and if something redundant is there, that will get removed so that it doesn't affect the any other path. Okay, and here if you look at the logic which I was telling there, that in this one, if I open it back, that here the count was incrementing because one we had got in the map, so that is here, this one. So this line count of 0, which is equal to count of 0 plus this line. Okay, this increments the counter based on the frequency of the complement of the running sum, which that is equal to current sum minus k. So we will take a complement of it, and if because whatever is the running sum, and we have to finally reach k, so that much we are subtracting. So we are taking a complement of it, and we are checking if that is already present in the map or not. If that is present, then we add it to the current count, and hence in this example the current count had become 2. Okay, and here we are checking, that means if the current sum is equal to current sum is equal to k, then we are incrementing the count of 0 by 1. This checks if the current sum is equal to k, then increment the counter accordingly. And here we have used the technique of memoization. The frequency in the prefix sum frequency hash map is used to store the frequency of each running sum encountered during the traversal. This technique avoids redundant calculation by allowing the algorithm to quickly determine the frequency of the previously encountered running sum. Okay, so I hope this complete solution is clear. Let me try compiling this code. So here we can see we have got correct output for this given sample. Trying to submit this solution. So here we can see it has covered all the test cases. So this problem has been solved successfully in Java. I have even prepared C++ solution. Let me try taking that here as well. The logic will be completely same. Only the difference, syntactical difference between Java and C++ that can be witnessed here. Here also we are taking the same mod. Then we have created a map, prefix some frequency, then counter is equal to 0, then calling this method, and it recursively calls by calculating all the possible paths, which makes the sum equal to k. Okay, so if you try compiling this code now, even with this we have got correct output. Let me try submitting this solution. So even with this C++ code, we have got the correct solution. So when we talk about the time complexity of the given solution, let me move to this Java editor again. So here the time complexity of this solution is in the order of big O of n, where n is the number of nodes in the binary tree. So if you break down all this complete logic here, so here we can see the DFS traversal visits each node once, making it big O of n, where n is the number of node. The hash map operations inside the DFS function, which is this prefix sum frequency, takes constant time for each node. Inserting, updating, retrieving from the map typically takes an average time complexity of big O of 1. So overall, the DFS traversal, since the DFS traversal and hash map operation both contribute to big O of n, so the overall time complexity of this algorithm is big O of n. Okay, so I hope both the solutions are clear. So I'll provide the link for this question and the link for the solution code in Java and C++ in the description box. Please do check that. That's all in this video. Please like, comment and share the video, and please subscribe to the channel for more upcoming videos. Thank you for watching.